Okay, let me quickly recall what we did last time. So last time we did the following things. So we talked about kind of Landau type of theory in kind of one dimension. So when our x is c star or t. Okay, so the multiparted complex dimension of x was one. So we kind of talked about relation functions that are kind of defined on some collection of holomorphic functions, and these correlation functions were computed in Landau-Ginzburg cycle with a certain mirror superpotential W, and here we kind of secretly assumed that in one-dimensional case our holomorphic top form was just dy, where y is just kind of coordinate on C or C star. Okay, so and we kind of did certain explicit computations in a very concrete example when superpotential was the mirror superpotential for CP1. So W took this particular form, and a kind of good section, image of a good section for this W was spanned by parallel functions, which are denoted by subscript capital I and phi subscript capital P. So one was just identity function in the space of holomorphic function, and another function was more complicated, Q times e to the minus A1. And we kind of computed certain explicit correlation functions. In particular, we kind of computed a 3-point function. This W was this 3-point function, which kind of match with kind of non-trivial multiplication structure in quantum cohomology rings. So this first 3-point function was just an ordinary intersection of kind of single 2 form and 2 zero forms, like 2 form in kind of H2 of P1. So they intersect over 1, and here we have like triple intersection of 2 forms from cohomologies of P1, and here the intersection is kind of over curve of degree 1. So therefore, the corresponding kind of Gromov-Fit invariant was equal to Q, and we managed to reproduce these 2 familiar expressions from Gromov-Fit theory using the rules of Landau-Ginzburg cycle theory and computing the 3-point functions. And furthermore, we computed the rest of correlation functions. So if we have like arbitrary number of phi p insertions, so then we showed that there is some kind of analog of divisor relation on Landau-Ginzburg cycle theory, and in this expression essentially is Q d over dq applied n minus 3 times to a 3-point function. And because 3-point function is the Q itself, so applying Q d over dq arbitrary number of times to it just gives us Q. And similarly, if we have like I insertion and kind of arbitrary good section insertions, so that expression vanishes, and that was analog of puncture relation in. Okay, so puncture relation in Landau-Ginzburg side theory, and that is a mirror of familiar puncture relation in chromophilia theory, and that was divisor relation Landau-Ginzburg side theory, and we kind of talked that the way we prove puncture and divisor relation could be generalized to higher dimensional Landau-Ginzburg side theory, modular, some subtlety. That there could be potential issues in definition of endpoint functions. And the last thing that we did on that class, we kind of studied dependence on kind of holomorphic function for this correlation function. So we noticed that if we just look at a 3-point function and say shift phi1 by kind of element from a gradient ideal, so for some kind of holomorphic function v, we shift phi1 by v times w prime. So phi1 plus v plus w prime kind of represents the same class in Jacobi ring. So phi1 plus v w prime, the class of this is the same as the class of phi1 in the Jacobi ring. So we just shifted by element of the gradient ideal. So with this kind of quotient definition, we shifted by arbitrary element from this IDW. And if we compute a 3-point function, then for 3-point function, regardless of what v is, we have an equality. And that kind of equivalently tells that the 3-point functions in LGS theory are defined on classes in Jacobi ring. So we can take kind of arbitrary representative of a classes, compute 3-point function, and get the same answer. However, the 4-point functions in LGS theory are not defined on classes. And furthermore, we kind of investigated sort of dependence on the shift. In particular, we computed the following 4-point function. So let us compute a 4-point function where here we just have like a different representative of a trivial class. So we just took like 0 holomorphic function and added to it v times w prime. And we took phi1, phi2, phi3. So these guys were kind of elements from images of the section. So we computed it, like computed the 4-point function, and we managed to simplify this expression to the following expression. That this thing is science. Okay, so science. So it's v prime, phi1, phi2, phi3. So the difference in this 4-point function is kind of controlled by 3-point function, and this 3-point function depends on v prime. So this kind of v prime dependence. So if v prime is not 0, so v is kind of real function, not just a constant, so not trivial function. So then generically this 3-point function is not vanishing, So therefore, generically, this expression is not zero unless we are the special situation that that v prime is zero. So given that v prime is non-zero, so this right-hand side is generally non-zero. So from that we make a conclusion that 4-point functions are not defined on Jacobian classes, and we really need to be careful like which representatives we use to substitute here, and therefore in our kind of mirror relation we need to explicitly specify like what kind of holomorphic functions we plug into Landau-Ginzburg-side correlation function to kind of obtain Gromov-Witten invariance from kind of A side of a mirror relation. Okay, so that was quick recap what we did last time. And I promised you that this kind of expression would be important when we will investigate the kind of definition of Landau-Ginzburg-side of theory in high dimensions. So let us give a definition. So endpoint correlation functions LGS theory. Let me give them a general definition. So LGS theory parameterized by X, omega central and a good section is given by. So okay, so here n is a few much bigger or equal to 3. Okay, so and let me even add endpoint correlation function. Yeah, let's just endpoint correlation function given by. Okay, so if we have a 3-point function, so then we have kind of high dimensional version of a residue formula. But let me start with kind of expression in terms of a critical point. So we additionally here assume that the kind of critical points of W are isolated. So there are like finite. So this set of critical points is just a finite set. So we take a sum of this isolated critical points. And here we do the following. So we take a product by 1, by 2, by 3. So just the 3 functions. Okay, so let me move lambda critical points. So we are evaluating this product of 3 holomorphic functions at point lambda. And here we need to kind of modify our formula. So for 1D version, we just have a division by W prime. And here will be the following expression. So it will be determinant with some dependence on holomorphic top form of kind of Hessian matrix of W computed at this critical point. So once again, critical point isolated, so it means that Hessian matrix is kind of full rank at all these critical points. So the determinant is not vanishing, and this expression determinant of its W is given by the following formula. So for holomorphic top form, so let me write it in explicit coordinates. So for holomorphic top form, we have components which are labeled by 1 to n. So n is dimension of x. And then we do the following thing. So we take another copy of this omega, J1 to Jn. And okay, so it's kind of non-degenerate holomorphic top form. So let us take omega inverse. Let us take two copies of omega inverse 1 to Jn, and here we just take partial derivative with respect to y1 j1 of w and multiply the similar type of partial derivatives all the way to answer. So that is kind of definition of this object. So that is kind of coordinate invariant statement of it, that you can use the holomorphic top form to compute a kind of holomorphic version of determinant of Hessian metric.
Okay. Excuse me. No, X is a general variety of isotopes.
No, X is general variety. So for Landau-Ginzburg side of theory, there is kind of no restriction on any toric. Like toric was our special assumption for A model side. So for B model side, so X is kind of arbitrary complex variety with kind of non-degenerate holomorphic top form. So in a sense, you can say that the pair X omega is generally non-compact collinear. So so that's why, okay, so arbitrary non-compact collinear. So here, this formula, it can also be written as a sort of higher dimensional residue. So here we take some kind of integral over half-dimensional contours in this complex n-dimensional space. And so phi1, phi2, phi3. And then here, story is a bit more complicated. So for residue, we need to take the product, the AW, and we also need some powers of holomorphic top form. So there is some kind of version of the residue formula where the gamma n is a contour given by assumption by the following formula that we take kind of norm of this DAW, and you can say that this norm equal to some positive number. So we are kind of not going to actively use that residue formula, at least. Okay, so we're going to use it in kind of our proof of invariance of four-dimensional. No, sorry. Even in that case, so in principle, like we can kind of use just this formula, which is some of the critical points, and I think in all cases that we're going to discuss in our course, we're never really going to use explicitly this residue formula. So that's why, like for now, you can think of it as some kind of extended remark that there is a way to generalize simple residue formula from one-dimensional case to higher-dimensional case, but for now there is kind of no real usage of it, at least in our course. Okay, so that was kind of extensive generalization of a three-point functions, and then for higher point functions, they are usually defined recursively. So phi1 to phi n. So here, that's what we would call LGS recursion with respect to phi n argument. So before we proven symmetry, we need to kind of specify which argument we use to perform the recursion procedure. So this one is W, phi1 all the way to phi n minus 1. So here we shift W by phi n and take kind of derivative of this term and so equals to 0. that one term, and then here usually we have a contribution from contact terms. So that will be one. Here somewhere will be contact terms between phi t and phi m, and one, and compute with them undefined. That is kind of generalization of a definition of endpoint function. And now I need to kind of supplement this definition with this kind of construction for contact terms, and construction works in the following way: the contact term between phi and phi tilde is constructed in the following way. So it's kind of holomorphic divergence of a vector field V, and the vector field V obeys the following property that V applied to W. So that is some holomorphic function, and this holomorphic function, which is trivial in Jacobi, equals to phi times phi tilde minus kind of this section applied to phi. Okay, maybe I should now not skip some reflection. Phi times phi tilde. So as we talked last time, so if I just multiply phi times phi tilde and subtract and good fraction from a class of this product phi tilde, then this expression, the class of phi tilde is the same as the class of this thing. So therefore the class of differences is a trivial class. A trivial class means that it has some representative, which is a vector field applied to our superpotential. So in the case of one-dimensional Dow-Ginzburg-Saito theory, so this representative is unique because we can just divide by W prime and get the unique expression for it. So in high-dimensional case, E is not unique. And therefore, kind of W phi tilde is not unique. And therefore it implies that we need to verify correctness of GS. So if kind of a piece of procedure that is used to define this recursion is not uniquely defined for pair of functions, then we need to verify that somehow this non-uniqueness doesn't affect the answer for endpoint function. And that kind of issue of correctness, it sort of precedes the kind of symmetry of endpoint function. So before describing symmetry of endpoint function, we need to kind of carefully investigate correctness. But before this, just to give like full definition, so let me kind of give definition of this holomorphic divergence. So if I have holomorphic top form, I can apply kind of holomorphic Lie derivative with respect to vector field V. So this will be once again a kind of holomorphic top form on X. And because it is holomorphic top form and it's non-degenerate, so we can write down it in the following way. So that is some function multiplied by the holomorphic top form, and because omega is non-degenerate, so we can get this function by applying omega, by dividing by omega, applying omega minus 1 to LV of this omega. And this function given by this procedure is nothing but is our definition of holomorphic divergence of a vector field, because it's just a generalization of a divergence of a vector field in kind of ordinary differential geometry, where instead of holomorphic top form, we just use a volume form to take a Lie derivative of a volume form. That is generalization. Divergence of a vector field with respect to volume form. So where divergence is mu. So vector field V with respect to volume form mu was +1 here, -1, and V line V. And in kind of special case where either volume form or holomorphic top form, some special case. So if we happens to choose our coordinates such that the holomorphic top form is just kind of a wedge product of n holomorphic coordinates, so it means that the coefficients of the function in front of this basis is just a constant function. So then this holomorphic divergence just became kind of usual formula when you take the partial derivatives of components of a vector field and take a sum of this partial derivative. And this formula is probably familiar formula for say divergence of a vector field in three-dimensional Euclidean space from some courses, maybe course in physics or course in differential geometry. The divergence of a vector field in three-dimensional space is like sum of its partial derivatives. Okay. So now at least I have all objects well defined on the board, and now I can proceed to this important part. This is to verify correctness of that definition.
Excuse me. Why V is a vector field?
V is a vector field because like elements of gradient ideal are kind of labeled by vector fields, because gradient ideal is kind of generated by kind of partial derivatives of W. So it means that the elements here is some kind of dkw in local coordinates. So then if I kind of want to covariantize this definition, so if I kind of try to make this definition coordinate invariant, so then as I change dkw, like as I change my coordinates, so this gradient ideal, the generators will change by Jacobian, holomorphic Jacobian. So therefore, to kind of talk invariantly about elements of gradient ideal, I need the coefficients to change by inverse power of Jacobian. So and kind of collection of n holomorphic function changing under coordinate transformation by inverse powers of Jacobian are components of some holomorphic vector field. So this kind of key components of holomorphic vector field V in coordinates. Right. Okay, so that's why this vector field, like physicists say even simpler, like you have a kind of a collection of functions with one upper index, and then what it can be just a holomorphic vector field. So here we kind of can say it in a bit more invariant way. Okay. So correct. Okay, so let us kind of, before we will prove a general proposition that the definition is correct, let us verify correctness for a four-point function. So let me put it in lemma. So recursive, let's say, LGS functions are well defined. Okay, but before going to this lemma, okay, so let me give you, before going to this lemma 1, let me first prove some technical lemma 2, which kind of quantifies the non-uniqueness in CW. So the statement is the following, that okay, now we go to formulation, so let me carefully use it. So let me call delta CW is just a kind of non-uniqueness in the CW, and the statement that delta of CW is holomorphic divergence of P applied to W or some holomorphic by vector P. So it means that kind of regardless of which kind of vector field I choose to compute my CW, that all the difference between kind of pairs of such CWs, so that is CW computed by some vector field V, and difference to CW computed by some other vector field V prime. So this kind of V and V prime, so they both satisfy V W equal to that part. So equal to that part in the definition. So if I take like two solutions V and V prime to that equation and evaluate difference of contact terms for V and V prime, so then this difference that I denoted delta CW, so that is kind of ambiguity in CW, so it has this nice general structure that it is holomorphic divergence of some bivector, so that will give me a kind of holomorphic vector field, and this holomorphic vector field is applied to our holomorphic function W, and that gives me another holomorphic function. So ambiguity in CW is kind of given by holomorphic functions of this form, that they are parameterized by this special object, which is kind of holomorphic vector. Okay, so that is lemma. So now let us proceed to proof of this lemma. Okay, so the proof is kind of straightforward. So it's kind of in part it's already written on the board. So we want to kind of investigate the pairs of V and V prime that obey this property, that taking kind of applying V to W and applying V prime to W gives us the same answer. So that implies that delta V, which is defined by V minus V prime, is such that delta V applied to W is 0. So in a sense, like this delta V is a symmetry of this function W. Okay, so now what can we say about symmetries of holomorphic functions? So in general, we can't say anything specific. However, our W has an additional property. So we have like this additional property that the critical points of W are isolated. And isolated critical points will give us a control over this delta V. Okay, so now let me work in components. So it's delta V K, V K W. So now let me apply a partial derivative with respect to some other arguments like dj applied to this expression. So this expression itself vanishes, then the partial derivative also vanishes. So it's dj of delta vk, vkw plus delta vk, vk, dj. So there's a partial derivative, so they are commuting, so I can write them in arbitrary order. Okay, so this thing is still 0, and now let me do the following thing. So let me compute. So this partial derivative vanishes everywhere. So let me compute it on a critical locus of W. So restriction to kind of critical locus of W, this collection of critical points, still make it 0. But now here we have partial derivative of W restricted to critical locus. So this whole expression vanishes. So because it's like contraction is 0. And here we will have what? We will have like kind of delta Vk, Vkw at the critical locus. And this expression is kind of what we call a Hessian matrix or holomorphic Hessian matrix. So that's what we usually call like D2W. And restricted to a critical point, so it's D2W evaluated at some critical point. And once again, because critical points are isolated, so the kind of rank of D2W at a critical point is kind of maximum. So because this matrix is a maximal rank, so then kind of here solving this equation kind of implies that the only solution is delta Vk should also vanish. So that delta Vk at critical point should better be 0. Okay, and if delta Vk at the critical point is 0, so then delta Vk should have the following structure. So it should be some kind of tensor with two upper indices contracted with partial derivatives of W. So clearly this way is kind of obvious, and that is clearly a sufficient condition for delta Vk of this form to satisfy this property. So in a case when everything is kind of over polynomials, when we kind of in algebraic setting, so it's also kind of easy to turn it this way. So in case of holomorphic functions, so this thing might be a bit more complicated. So for now, like I kind of ask you to trust me that if I kind of do a holomorphic setting, that holomorphic setting is like an algebraic setting, and the vanishing of delta Vk at a critical point kind of is equivalent to delta Vk having this form that it is kind of partial derivatives of W contracted with some temp. So that was computation coordinates and kind of coordinate free notation. So we would say that this vector field delta V is a kind of y vector applied to a holomorphic function. So P is just some y vector. So that gives us a kind of under this special assumption that critical points of W are isolated. So we have full control of what kind of delta V's satisfy this equation. That all solutions to this equation, they have this very particular result. Okay, and now if you have explicit form for delta V, we can evaluate delta phi.
Excuse me, I confused with the definition of V. Is this the definition of V?
Yeah, so that is the definition of it, yes.
So if we fix SW, is
So V is still not unique, because there can be different holomorphic vector fields satisfying this equation.
they are equal in which?
In functions, in holomorphic functions. Because in classes, it's just trivial. So on the left hand side is a trivial class, and on the right hand side is a trivial class. So we want this equality in a space of holomorphic functions.
But the right hand side is fixed.
Yes.
So why the left hand side is not?
Okay. So let me erase something and give you more explicit example. So let's say that the tower X is two-dimensional. So we have coordinates of y1 and y2. So then in coordinates, this equation equals to the following. It's like d1, v2, v1, d1w plus v2, v2w equals to some right hand side. Let me just call it capital R. So right hand side is some fixed function. So what we want to solve for vector field v for fixed right hand side. So suppose I found like some solution. So then let me look at the vector field u with the following components. U1 is v1, but here I add just d2w, and for u2 I take v2 and subtract d1w. So that is kind of my vector field u. That's the definition of u. So now let me compute u applied to w. So by definition is u1 d1w plus u2 d2w. And let me now substitute components. So this will be like v1 plus d2w multiplied by d1w plus v2 minus d1w multiplied by d2w. So now what I see? So I see two types of terms. So I see like these terms that give me a familiar v applied to w. And then there is like additional terms, but additional terms is like d2w multiplied by d1w from this term. And another term is minus d1w d2w from this term. And they perfectly cancel. So therefore I got a pair of vector fields v and u. And they are different vector fields because I added to components some kind of partial derivatives of w which are non-zero. So away from critical points, they are different vector fields. So on critical points, they kind of coincide. But away from critical, everywhere on X, they are different vector fields, and therefore they give me two distinct solutions to that relation. And there is no kind of canonical way to choose like some kind of V among this family like canonically. So to say that there is some kind of special choice which I can use in my definition. So there is no special choice. So therefore I need to deal with this kind of consequences of kind of arbitrariness of this. But luckily for me, kind of arbitrariness of this V is kind of controlled by vector. And in this example, so in this example, I kind of choose my u and v. So u minus v, like u1 minus v1 was kind of d2w, and v2 minus v2 was minus d1w, and this kind of general formula is we take a constant by vector. Constant by vector is just anti-symmetric symbol. So epsilon ij is defined as epsilon 1, 2 is 1, epsilon 1 is minus 1, and the rest of the components are 0. Just anti-symmetric tensor in 2 dimensions. And so I choose like a simplest bivector, just a kind of constant bivector that is anti-symmetric in its arguments, because it's kind of element of here maybe a formal definition, so it should be like lambda 2 of holomorphic vector fields on X. So bivectors, it's kind of like a tensor. It lives in kind of second tensor power of vector fields and anti-symmetric. So it lives in symmetric tensor power on vector fields. So here, and this is kind of simplest bivector, which is just constant bivector in our local coordinates. But the same kind of argument, the same cancellation would work for arbitrary bivector as long as it's antisymmetric. So for any kind of antisymmetric pi ij, so this argument would still valid. And that kind of given additional assumption that critical points are isolated, we can indeed kind of confirm ourselves that are all possible solutions.
Yeah, but this pi in general is now we just know it's a
It's a bivector, so it's antisymmetric.
why it's antisymmetry. Yeah. And how can we see it's antisymmetry? We just know there exists such pi as a tensor.
No, it should be antisymmetric. Okay, I erased my computer. Okay, so we have like this property that delta V restricted to critical W is 0 because critical points are isolated. So clearly, if I choose delta V of this form okay, you say that if I choose arbitrary symmetric, like arbitrary bivector, arbitrary tensor with kind of proper with the components like in the second tensor power of vector field, then this condition would still hold. Okay, that's a good point. Okay, so then there will be another problem that this thing was a consequence of that star. So it was kind of star that it was implication of a star. But what we want solutions to a star. So for implication, we kind of got this answers with pi arbitrary to tensor. But now we still want to use this answers and substitute it into star. And that means that delta V applied to W, which is pi contracted with this kind of 2.
Oh, I see. So
Partial derivative.
So pi.
So this thing should vanish. And the only way to achieve this is to choose pi antisymmetric. And yeah, okay, so that's a good point that we need to recall that here it was just an implication of an equation that we want to solve, but not the equation itself.
I'm just asking a very simple question, just like if pi contains some symmetry part, then it will be non-zero.
Yeah, so then it will not solve star.
Okay.
Yeah, so and what we want to solve star.
Just a second. If pi contains some symmetry part, can this partial W contain some zero component?
No, because if it contains symmetric part,
then there will be some component of W, such partial W is 0.
Yeah, but we have control where partial W vanishes. So we know that. Yeah, so that will imply that symmetric part multiplied by some partial W's should vanish everywhere. And I think that would kind of contradict with critical points being isolated. So,
Yes, I guess so. And but still, there is a question here. This pi seems to be defined on critical locus. So
no,
we
no,
need
no, no, no. So here, yes, pi was kind of in this kind of when we solved implication, we solved implication only on a critical locus.
Yeah.
But then we kind of extended
Yeah.
solution of implication to an ansatz for delta V everywhere on X by kind of extending this pi to holomorphic bivector everywhere on X. And then we substituted this ansatz into our original equation and got that pi extended.
Is there some analytic problem that maybe there is some obstruction that we
Yeah, so that's why I said that all this kind of works nicely when we work in polynomials, so in kind of algebraic setting. But for analytic setting, at least, okay, for now I don't have like a complete proof. So for now the best argument I can offer that if we can do like polynomial setting or some kind of serious expansion setting, so then you can kind of carefully prove this. But in analytic setting, I kind of don't have a careful proof.
I mean, the same setting is how can we prove that there exists a global bivector field pi such that when we restrict to a critical locus, it satisfies such condition. So here we
No. So that is not condition on pi. Like pi can be arbitrary on a critical locus. So it's delta V equals to some kind of arbitrary pi.
Yeah.
So that's why there is no restriction on pi on a critical locus. It's like a bivector that is restricted to bivector on a critical locus. Like any.
But this vanishing condition delta V.
It's vanishing on delta V.
Yeah.
And the vanishing is kind of, it's not constraining pi. So it vanishes for any pi.
Yeah. But from this vanishing, we know there exists such bivector over critical locus.
Yes, but it's not unique.
This,
like it's kind of there are many bivectors.
Yeah.
So there is like a whole family of bivectors on a critical.
We fix one set of bivector over critical locus.
Yeah, but
then we need to extend them to the.
Yeah, but we have like here pi is like a full family of bivectors on a critical locus. So there is no restriction on pi. So any bivector on a critical locus is a locus. So and therefore, if there are no restrictions on pi, there is no problem of extension.
I see. Okay.
Because
pi is global defined. Pi is just
pi on critical locus is arbitrary, and therefore it can be like extended globally. It's like if you have like some restrictions on a function in critical locus, then you may ask a question like whether there is some consistency.
Yeah, I know the problem. If delta V is a tensor acting on W, but when restricted to critical locus, it's like antisymmetric. But at everywhere else, it's not necessarily antisymmetric. How can
No, but we still need to solve star. So kind of yes, it is true that on a critical locus pi is not necessarily antisymmetric. So therefore you kind of take this pi which is not necessarily antisymmetric, extend to kind of arbitrary two tensor with two upper indices everywhere. So that there are no kind of conditions. And then you kind of take this kind of pi's that solve this implication of critical locus. And use them to kind of further verify star, and then when we substitute arbitrary pi into star, you notice that we should like further impose conditions on pi. But because here we have like a more freedom on pi, so there was no conditions on pi, so therefore imposing conditions like away from a critical locus, there is no problem to kind of take a pi with conditions away from critical locus and restrict back on the critical locus. So that is perfectly fine. Okay, I think now it's a good time to make a break. And then after the break, we will. Sorry. No. Let me say one more thing because I want to finish proof of the lemma. So far I kind of computed delta v, and there is kind of last step that the delta c is essentially what is holomorphic divergence of delta v. So that is kind of by definition, and here we just apply holomorphic divergence to this vector field which is pi of W. So here we not quite getting a statement of a lemma, and here we need to do a bit more work and use this antisymmetry of pi one more time. So here let me once again work in coordinates. So in coordinates, this function takes the following form. So it's dk by kl ELW. So that is, we took this vector field in components, so it's delta v k in components, and we took its holomorphic derivatives in coordinates where holomorphic vector top form takes this. Okay, let me call it special coordinates. In special coordinates, when holomorphic vector form is just product of DWs. Okay, and here we got two terms. So one term is dk by kl applied to dlw, and there will be another term which is by kl, and this derivative is w. And now, because pi kl is antisymmetric, so this term vanishes. So therefore, antisymmetry of pi kind of allows us to eliminate one of terms, and this remaining term, it kind of has a structure of some vector field constructed from holomorphic divergence in the special coordinates of pi, applied to W, contracted with partial derivatives of W. And this expression is kind of, this expression is special coordinates. So at least in special coordinates, I kind of proven the statement of this lemma that delta CW of phi has this structure that it is a kind of holomorphic vector field constructed as holomorphic divergence of some bivector applied to W. So here, okay, formally you need to kind of further argue that this statement in a special coordinate kind of holds invariantly in kind of coordinate free notation. Okay, but for now, kind of working in special coordinates would be okay. At least in kind of physicist approach, like physicists always work in special coordinates, and in our kind of explicit construction for endpoint functions in Landau-Ginzburg side of theory, so we know like explicit form of the special coordinates, and the mirror that we will construct is kind of naturally come, so naturally give us Landau-Ginzburg side of theory in this special coordinate. So therefore, for a purpose of kinds of tropical mirror symmetry, proof for special coordinates is just fine. But kind of for the sake of general theory, we in principle need to kind of carefully supplement this argument by another argument of kind of doing this thing in coordinate free way. Okay, I think now we want to go to a break. So we finish with proof of this lemma, and we kind of ready for our lemma 1, which is invariance of the 4-point functions. Sorry, not invariance. well-defined Folkman function, which precedes the invariance limit. Okay, so let's make 7-minute break, like 10 till 11. Okay, so let us continue with the proof. The invariance, the well-definedness of the 4-point function, yeah, 4-point function non-Gilbert fallacy. Okay, so we have this formula, recursive formula for n equals 4. So that is our 4-point function. And in this recursive formula, we have what? So we have this derivative term. So derivative term is kind of insensitive to any contact terms. So derivative term is kind of okay. Derivative term is okay. So potential problem could be with a contact term contribution. But contact term contribution is kind of doesn't come in the form of just a contact term as a holomorphic function, but in the form of some 3-point functions computed using these holomorphic functions as an input. So we have a typical term which is like this. So we do a kind of recursion in phi 4. So we have like a typical contribution to a contact term is like this. So the typical contribution is some 3-point function where we have one contact term and kind of two other phi's, like phi 1 and phi 3 in this particular. So now, if I, for this contact term, if I choose the kind of a different holomorphic vector field to compute a contact term, so then I would get some kind of, let's say, variation of this typical contribution. And variation of typical contribution would be a 3-point function where we have like phi 1, phi 3, and variation of this contact term. However, for variation of a contact term, we have our lemma that kind of gives us control over variation. So it's phi 1, and here we have this divergence of phi applied to W phi 3. So for this 3-point function, let us notice that this divergence of phi is just some holomorphic vector field. So this expression is essentially has this form. So it's some kind of, call it U of W phi 3. And now we notice that here we have a 3-point function. We have functions phi 1, phi 3, and another function u of w. But this function u of w has this additional property that it kind of represents a trivial class in Jacobi ring. And earlier we kind of observed that for 3-point functions, okay, so we kind of carefully observed it in one-dimensional setting. The 3-point functions in one-dimensional setting, they are kind of defined on the classes in Jacobi. So similar holds in higher dimensional case. So we can call it, yeah, maybe I should call it lemma 3. That's the kind of 3-point functions are defined on Jacobi rings. Jacobi ring class. And indeed, kind of proof of lemma 3 is sort of straightforward. So we just compute a 3-point function of a difference. So now in high dimensional case, we have some kind of u of w, phi1, phi2. And for this 3-point function, we have our favorite formula, which is sum of the critical points. And here we take a product of 3 functions. So it's phi1, phi2, and let me use like some local coordinates and write down the first function as uk dkw. And here we divide by this holomorphic determinant of Hessian match. Holomorphic. So here we observe the following thing. So holomorphic Hessian matrix, as we said, is kind of full rank. So determinant is non-zero at each of the critical points. So while dkw evaluated as a targeting critical point is 0. So therefore, in the numerator, like phi1 and phi2 are just kind of holomorphic functions. So they don't have like poles anywhere. So they don't, in particular, they don't have poles at the critical points. So therefore, here phi1, phi2 have finite value at the critical points. This determinant also has kind of non-zero value at the critical point. So therefore, in this sum, we have like some kind of multiplicative factor which is 0 at each single critical point, because this factor is just kind of linear combination of partial derivatives of w, and each partial derivative of w at a critical point, like for all k, all these partial derivatives vanish. So therefore, each single term in this sum vanish, and this finite sum of 0 terms is also 0. So that is kind of easy lemma 3, which kind of generalize our observation in one-dimensional case. The 3-point function is kind of well defined on Jacobi ring classes, and that kind of matches with what we expect from mirror symmetry, because 3-point functions they kind of determine multiplication in Jacobi ring, and we already know that multiplication in Jacobi ring kind of matches with multiplication in quantum cohomology. So at this level, it's kind of isomorphism of rings, and then kind of using this lemma 3 that we just proven. We see that ambiguity in a 4-point function due to kind of change in a choice of contact terms is kind of this very similar form, is a 3-point function where one of the arguments is from 0 class in Jacobi. So therefore, if we independently vary like the 3 terms, each of the term kind of vanishes independently. So each of the term in variation vanishes because of this special property of 3-point function. So that kind of completes the proof of lemma 1. So it kind of took us a bit of extra intermediate lemmas like lemma 2 and lemma 3 kind of completed, but nevertheless we kind of verified that despite the contact terms are not being defined uniquely, but non-uniqueness kind of vanishes in Jacobi ring, and that's why it doesn't affect the answer for the 4-point function, because this non-uniqueness is kind of substituted into 3-point functions which vanish for trivial class in Jacobi ring. So here the natural question is, okay, so for 3-point functions, this thing looks like a special case, and we know that the 3 and 4-point functions are different in the sense that the 3-point functions are well defined on classes, but 4-point functions are not well defined on classes. So maybe if we go to say 5-point functions, we will run into real problems, because for 5-point functions we need to kind of investigate the kind of the contribution to the 4-point function from this delta C of this form. And once again to prove, and the case of 5-point functions is the same as the general case. That going from kind of 4 to 5 point functions, we need to kind of modify our proofs and make them more elaborate, but there is nothing interesting happens when you go to n-point function. So therefore, let me do the following thing. So I kind of really want to finish Landau-Ginzburg-Saito theory today, because unfortunately the course is not quite about Landau-Ginzburg-Saito theory. So that's why I will kind of send you lecture notes later today with this kind of careful recursive proof for endpoint functions. And today, kind of on a board, I will just do a kind of 5-point function case, and kind of recursive proof is essentially just kind of additional, it's kind of just some more careful application of the ideas from 5-point function case. Okay, so let me erase this lemma 3, which is kind of almost of this lemma. So now let me okay, so yeah, okay, so let me start right here. So okay, so in the case of n equals 5, so once again, the derivative term is not a problem, because we already shown that the 4-point functions are well defined. So taking the derivatives of 4-point functions is kind of well defined procedure. So therefore, the kind of typical variations of the typical term we have this form. So let me write it. Let's see whether I have a better notation. Okay. So in my notation, let me write it in the following way. So we have this delta CW of phi 1, phi, what we call it, phi 4, phi 5, and here it's like phi 1, phi 2, phi 3. Related to delta. So we have a 4-point function where we have like 3 normal observables, and one observable is this kind of variation of a contact term. So once again, using explicit formula for variation of a contact term. So here we have a kind of a vector field U applied to some W, and here with phi 1, phi 2, phi 3. So we have 4-point function of that. Okay, so I really want to keep the term. Let me erase a bit here and just kind of write this single formula. Because I really want to erase all. Okay, so now we have this kind of 4-point functions that kind of controls this ambiguity in contact terms. So let us try to kind of simplify this 4-point function. So kind of recall a couple of words ago, I kind of erased a formula that we derived in one-dimensional case. So in one-dimensional case, we had a formula like this, that such a 4-point function was actually related to a particular 3-point function, which was like v prime, phi 1, phi 2, phi 3. So that was kind of something that we derived for one-dimensional case, and it turns out that we can do a similar derivation in high dimension. So how we do this? So here, once again, 4-point functions are well defined. So 4-point functions are well defined. So we can apply Landau-Ginzburg-Saito recursion and then pick up kind of any vector field in the context. So kind of here we apply LGS recursion, and here we will do it with respect to say phi 3. Okay, maybe we should do with respect to phi 1 to just match one-dimensional computation. Okay, so we will get the following terms. So there will be derivative term, which is the three-point function u of w phi 2 phi 3, and here we deform w by phi 1. And so that's the quantity just recursion. And then we have three contact term contributions. So let me kind of organize them into two groups. So one contribution, when we have a contact term of u of w and phi 1, and phi 2, phi 3 remains as they are. And then there will be another contribution where u of w stays as it is, and it's kind of a contact term, say, between phi 1 and phi 2, and phi 3 remains as it is. And the very last term is kind of a term number 3 with 3 and 2 interchange. So let me first start with these two terms. So for these two terms, let us notice the following structure. So it's kind of u of w standing in a three-point function with some other functions like so. Here we have like some two holomorphic functions, phi 3, and some holomorphic functions obtained from a contact term. But the most important part that these two holomorphic functions, they come together with kind of u of w, and once again we have our lemma 3. So that is vanished, and that is vanished by lemma 3 because it's u of w, some other two homomorphic functions, and the three-point function evaluated with undeformed superpotential. So this w is the same as w here. So by lemma 3, this thing just vanishes. Okay, that is good. So we kind of get rid of two terms. So now let us let us transform so let us kind of transform the derivative term. So in derivative term, although we have a kind of three-point function with u of w, but kind of the argument of the vector field w is not the same as a kind of superpotential used to compute three-point function. So here it's w plus epsilon phi 1, and here it's just w. So let us do the same thing as in one-dimensional case, kind of add and subtract. So we still have like d of the epsilon at epsilon equals 0. And now we do addition and subtraction. So let us kind of add epsilon phi 1 to a w to make the kind of argument or to make a holomorphic function to which a vector field u is applied to match this with a superpotential which we use to compute three-point function. And then we subtract the difference, and difference is kind of proportional to epsilon. So it's a u applied to phi 1, phi 2, phi 3, and computed once again in a theory with deformed superpotential. So once again, kind of this term is 0, and that is once again our lemma 3. So what we left with, we need to take partial derivative with respect to epsilon, evaluated epsilon equals to 0 of this last term. So here, there are two places with epsilon dependence. So kind of one place is this factor of epsilon in front of it. There's one epsilon place for epsilon dependence. Another place for epsilon dependence is a deformation of the superpotential. So therefore, d over the epsilon derivative can hit kind of epsilon dependence in one of the two places. But if it happens to hit epsilon dependence in superpotential, then the further evaluation of this expression at epsilon goes to zero, just vanishes. So kind of epsilon dependence on this 3-point function is just smooth, so it doesn't have any poles in epsilon. So therefore this term epsilon multiplying it will just make whole expression zero. So therefore, for this derivative, the only option to get a non-zero answer is that d over the epsilon should hit this epsilon, and the second epsilon should be set to zero. So therefore, this expression just equal to minus u of phi 1, phi 2, phi 3, evaluated at tau. And that is kind of okay. So it's one of the intermediate steps of high dimensional version of that formula. Okay, so that is evaluation of the yellow term. So yellow term is non-zero, but we can kind of turn it into some sort of 3-point function, which kind of simplifies it a lot. I think there is no epsilon derivatives, so everything is pretty connected. So now the last term is this green term, for which we need to compute a contact term. So let me the following. So let me write this motivational part. So yeah, and let me also to save some space just erase the left. Okay, so we have a contact term Cw with u of w and some function phi 1. Now, so let us use our definition. So we need to take holomorphic divergence of a certain vector field V, and vector field V should be a solution to the following equality. So we need to multiply two of these things together and subtract a good section of a projection of their product. Okay, so let's start with this kind of is the product itself. So u of w phi. So what would happen if we evaluate a projection of this thing? So projection of kind of product is a product of projection. The projection is kind of homomorphism of rings. So I can as well rewrite it in the following way, that I project a first kind of term in the product and then kind of multiply it by projection a second. So this multiplication is in functions and this multiplication is in classes. And then now, once again, I notice that this is kind of a representative of a trivial class. So kind of projection projects it to a trivial class, and this trivial class multiplied by projection of something, and it's kind of zero is the zero class is zero of multiplication. So therefore here we would get a zero class, and kind of by construction, good section applied to zero class is just zero function. Or more generally, good section applied to a constant function is that constant function. And kind of a particular case of constant function is zero function. So therefore here we explicitly evaluated that part and turn it to be zero. So now we need to solve this remaining equality that v of w is u of w times phi 1. So and for this there is one kind of possible solution. One possible solution is just take a vector field V, which is equal to a product of a scalar of a function phi1 and a vector field U. So then kind of by definition, the kind of application of such product vector field to some function will be a vector field U applied to this function multiplied by phi1. So this expression product of functions, so I can put phi1 to the left of U of W. Okay, so and our kind of idea, because we will substitute these contact terms into kind of what into 3.5. I'm confused. Sorry. 1, 3, 2, 3. So to get to evaluate this term, we will once again, this contact term is not uniquely defined, but this not uniqueness was already proven that it's not an issue. So 4-point functions are well defined. So therefore here I'm kind of all over to take arbitrary solutions that I can guess, and there is one kind of obvious solution that V equals phi1 times U. So therefore now the last step is to take a divergence, so to compute these contact terms. I need to take homomorphic divergence of this vector field, which is phi1 times U, and here it's once again kind of ordinary divergence. We have the property that divergence of the functions multiplied by vector field, it has the following structure. So it's kind of this function acting on a vector field plus this function multiplied by homomorphic divergence of a vector. So this equality is kind of straightforward if you write it in local coordinates. But I think you probably might know it from course of differential geometry. I think some courses it is discussed. But if you don't know, just write it in components, and then it became just some kind of simple rule applied to a product. Okay, so that gives us explicit computation. So now let me kind of erase this last term, which is 0 anyway, and in kind of space that is free, let me kind of write down what we get after we computed this contact term. So it's U of phi1 plus phi1 divergence, homomorphic divergence of U. So that is the first argument, and we have phi2, phi3 as a remaining component. So that is evaluation of this, or simplification of a term when we explicitly evaluated contact term. Okay, so now what we have this green term and this yellow term. So that's the only remaining non-zero term. And here we immediately notice that we have like the similar contributions like U of phi and minus U of phi in the same 3-point function with phi2 and phi3. So that gives us immediate cancellation, and we left with the following formula, that is phi1 multiplied by homomorphic divergence of U and 3-point function of that expression with phi2 and phi3. And here you can recognize the formula that I already wrote at a race twice today, which is the formula which is kind of higher dimensional version of the formula that we derived at the end of the class last time. But here, instead of, in one-dimensional case, instead of this holomorphic divergence of a vector field, we just had like V prime, which was holomorphic divergence in a special local coordinates. Okay, but here we derived it in kind of general setting for general omega, general and Gaussian cycle theory. Okay, so this term is still non-zero. So yes, we kind of simplified it to a 3-point function, but it's not a 3-point function something like vector field applied to W. 3-point function of some three functions that doesn't look zero. However, let us recall our answer for contact length. So let me erase all that part for some technical computations for contact length. So now once again we kind of recall the formula for delta C, that we kind of substituted delta C as a U of W, but this U was not arbitrary holomorphic vector field, but it itself was originated as a divergence of some bivector. So now, kind of, because we want to somehow deal with that remaining term, so let us see whether this additional detail about holomorphic vector field would help. So divergence of this holomorphic divergence of this vector field is like holomorphic divergence applied twice to this bivector. And in some kind of proper sense, so there are like two ways of arguing why it is zero. So one way is to just use special coordinates. So in the special coordinates, like the components of U is just the L by KL, and kind of divergence of U is just dk UQ, and then substitution will be like dk DL by KL, and then pi KL is antisymmetric, and dk DL they are symmetric. So therefore it vanishes. So that's kind of one way is kind of to use special components to show this. So another way, which is more familiar from a standard differential geometry. So in a standard differential geometry, so kind of divergence of a vector field, it can be expressed as some kind of d star acting on some form which you can associate to a vector field. And kind of for a bivector, it's the same story. The divergence of a bivector, it kind of related to a kind of d star up to some times Hodge star, the RAM operator Hodge star, and kind of if I try to apply divergence twice to a bivector, so that is the same as kind of applying d star twice to the corresponding differential form, and d star kind of square is kind of up to a sign is star d square star, and this thing is also zero. So that is kind of another way of arguing that this divergence of holomorphic vectors of holomorphic bivector, that this thing vanishes. So this kind of second way is sort of coordinate free way of arguing, and kind of approach one is more straightforward and more explicit, but it kind of relies on first writing down everything in special coordinates, and then noticing that divergence vanishes because of antisymmetry of pi KL in the special coordinate. So whenever way you take, it's kind of gives you the same answer that here, yes, delta C is a vector field applied, holomorphic vector field applied to a function W, but this vector field is kind of divergence-free vector field. So it's divergence-free because it is itself its divergence of some bivector. And therefore this term kind of finally vanishes. and that was kind of a long way of estimation of a variation of a typical term. So variation of a typical term in kind of Landau-Ginzburg-Saito recursion for a 5-point function is a kind of 4-point function of that form, and we kind of explicitly first turned this 4-point function into this 4-point function which contains a divergence of a vector field, and then we observed that the vector fields that control kind of variation or ambiguity in the contact terms, they actually have this additional property that that they also are divergence-free vector fields. And kind of the same ideas can be used to prove for general n, that on the first step you kind of assume that the correlation functions for n minus 1 are well defined, and you get some kind of analog of this relation, and then you kind of still argue that divergence of a vector field is zero. Okay, and that is just some simple kind of recursive proof for n. Okay, so with this kind of long story with some lemmas and cases, so finally we managed to confirm that our definition for correlation function of Landau-Ginzburg-Saito theory is kind of is correct. So in a sense that the endpoint functions are kind of insensitive to ambiguity in computing contact terms that enter the recursion. So it turns out that this ambiguity doesn't affect the correlation function. Okay, how do we do this time? 41. Yeah, maybe it's a good point to maybe make a break and or take a couple of quick questions, because I don't want to start. So the last kind of item on today's agenda is symmetry of endpoint functions, and it's better to make break now and start the symmetry later. So I hope I convinced you that that this definition, that this Landau-Ginzburg-Saito procedure is well defined. Okay, so if there are no questions, let's make 8-minute break. So it's break till 11:50. now that part we can even erase that part, so we don't need to worry anymore. Oh, non-linear conceptual. Yeah, so our strategy for kind of functions are symmetric. Given that we factor f that W, which was an F class with Jacobi ring to some specific representatives. So that the good section obeys the following formula K1 W. Just write it and then I will. So that this thing vanishes, and that is for kind of arbitrary pair or arbitrary classes in Jacobi. So that condition we will commonly tell that the first sign of residue pairing vanishes on the image of good section. So here, like we apply good section to two classes, so we get two elements from the image of a good section, and we kind of demand that at certain K1, that is this first status residue pairing, vanishes on this image. So for K1, let me kind of give you explicit formula in one dimensions. So okay, so in one dimensional case, K1 has, okay, let me kind of give you hierarchy. So we kind of had some residue formula for 3-point functions in one dimensional case and to high dimensional. So there is a way to kind of use this residue formula to define a pairing on on functions, on homomorphic functions. So, and this pairing is what is denoted by K0, and in one-dimensional case, it is given by the pairing has two arguments, phi1 and phi2, and it is given by the following formula in one dimension. So we just multiply phi1 and phi2, and then kind of divide by W prime, and take this residue integral over some contour that is far away to enclose all zeros of W. And this formula has a kind of an alternative expression in terms of critical points for W, assuming that they are isolated, so it's just phi1, phi2, and here divided by W prime, and all of this kind of summed over this critical. So that is K0. And in a sense, the 3-point function can be expressed of this K0 if different color. So we can express 3-point function in the way, so this is K0W applied to say phi1 and the product of phi2 and phi3. So we can use this pairing to express 3-point function. So that's why here we don't introduce anything new. So the new next kind of pairing in some family. So there will be a family labeled by positive integer like kn of W. But let's for now do it step by step. So let me give this formula for K1. So for K1, the kind of residue integral formula okay, so it's phi1 prime phi2 minus phi2 prime phi1, and here divided by twice W prime squared. And as a kind of sum over critical points, this formula has the following structure, and here will be W double prime squared with a factor of 2. And for enumerator, okay, have it here. So it will be okay. Maybe okay. I'm not sure about the sign because kind of have two types of nodes with slightly different signs. So let me kind of model the sign, which I might mess up a bit right now. So it's phi2 double prime, phi1 double prime phi2 minus phi2 double prime. So that is kind of familiar formula to kind of residue when you have like higher order pole. So what you do, you need to take like some derivative of your function in this, like when you sum over kind of higher order poles. So here it's like summation of poles, and here I just took derivative of this function, and I noticed that in this derivative, like generally we should have 4 terms, but the term like phi1 prime, phi2 prime is kind of going to cancel by phi2 prime, phi1 prime. And that's why among 4 terms, a pair of terms cancel it, and I just left with the 2 terms. So that is kind of K1 pairing, and precise statement about symmetry is that as long as we choose our good section SW, so far we don't have any constraints on SW, like any SW would do to define a context. However, now if SW satisfies this additional property that this first residue pairing evaluated at kind of at image of SW, so if it vanishes, then kind of this SW is kind of good section, and we can use it to define 4-point functions that also has this additional properties of being symmetric in all 4 arguments. Okay, so natural question like how would one kind of guess these formulas, and there is kind of 2 ways of doing this. So short story is that you can get this formula explicitly if you just kind of study. So basically the kind of proof of proposition works in the following way. So we consider 4-point function in 1-dimensional theory, and we kind of apply Landau-Ginzburg side recursion. Let make sure that I do the same. Yeah, so, and for now in Brookside recursion, we can do the following thing. So we can do recursion with respect to phi 4. So that it will be something like E over the epsilon equal to 0, and here will be W with respect to phi 4 plus contact terms. And then we want to compare the computation of the same 4-point function. But when we do Landau-Ginzburg-Sayet recursion with respect to different arguments, say phi 3. So the symmetry would imply that regardless which argument I use to recursive formula, the answer should be the same. So that is equivalent to being symmetric. So restoring symmetry means kind of arguing while Landau-Ginzburg-Sayet recursion with respect to different arguments give the same answer. So technically we would compare it with the following formula phi 3 plus contact. Comparing means that we will look at the difference. So we kind of expect to prove that this difference is 0. So let us study the difference and study it on the level of Landau-Ginzburg-Sayet recursion. So here we have kind of two very different looking expressions. Like it's some derivative of a 3-point function of phi 1, phi 2, phi 3 in a theory deformed by phi 4. And here we say have a 3-point function with 3 replaced by 4, but deformation also exchange. So now I need more space, so I will familiar with the definition. So let me way more space. And studying this difference, let us study it in kinds. So we have what 8 terms in this expression, like 1 derivative term and 3 contact terms in each of the expression. So first, let us look at difference in derivative terms. So let us derivative terms. So for derivative terms, we do the following thing. So we have explicit formula for 3-point functions. So let me put it in some color. So that would be derivative term difference. Derivative term the following. So once again, it's d over dx epsilon equal to 0. And here we have kind of two representatives, phi 1, phi 2, phi 3. And here is w prime plus epsilon phi 4 prime. And this constructs a similar integral phi 1, phi 2, phi 4. This line plus epsilon phi 3 prime. Okay, so let us just evaluate epsilon derivatives. So what would we get? Okay, so there will be minus sign because epsilon dependency is through denominator. So it will be phi 1, phi 2, phi 3, and here will be phi 4 prime, and here will be w prime squared. So that is epsilon derivative evaluated epsilon equals 0 of the first term. So derivative would give us square of denominator and phi 4 prime going into numerator, evaluating it. And similar here it's like phi 1, phi 2, phi 4, phi 3 prime divided by once again w prime squared. And we can combine these terms into single expression. So we can notice that phi1, phi2 over w prime square is kind of common for this thing. And here we have like phi3, phi4 prime minus phi3 prime, phi4. So here we notice that expression, it kind of starts looking like our first residue pairing. So it kind of contains some w prime square in denominator and contains some derivatives of the argument in numerator. But unfortunately, like as it's written right now, it doesn't quite k1 of something. So to get it into k1 of something, we need to add and subtract certain bits. So kind of let me skip this technical detail and just write an answer. So it's phi1, phi3, phi2, phi4. K1, phi2, phi3, phi1, phi4. Okay, so what you need to do, you need to kind of add and subtract some terms. Or equivalently, if you just plug in these arguments into K1, you will get like some kind of product of 4 phi's with a single derivative acting on one of the phi's, and then kind of if you properly combine these terms, then you will see kind of a lot of cancellations, and at the end of the day, derivatives would only fall on phi3 and phi4. So kind of this computation for change in derivative terms, it kind of already hints you that there should be some kind of new higher residue pairing controlling the answer. But for now, like here, we don't see any kind of good sections, and that is not surprising. Derivative terms, they don't know anything about good sections. So therefore, to get like this condition, which is some condition on a good section with respect to K1, we need to carefully the second bit of this expression, which is this contact term contribution. So contact term. So for contact term, double star. So in contact term contribution, there would be immediate cancellation of so there will be like 3 contact term in first expression, 3 contact term in second expression. But among these contact terms, so there will be kind of one contact term which is symmetric after replacing like phi3 and phi4. So both expressions would contain the contact term contribution of this type. When it's contact term between phi3 and phi4, and it has 2 interpretations. So we kind of expanded in phi4 and computed phi4 contact term with phi3, or we expanded in phi3 and computed phi3 contact term with phi4. So for contact terms, we noticed that the answer only depends on the product, so therefore it's symmetric in these 2 arguments. So therefore here essentially we are down to just 4 terms. And furthermore, we noticed that all these 3-point functions, they can be written in terms of k naught. So you can write it like this. So it's phi1, phi4, phi2, phi3. So that is one contribution here, and then it will be like k naught w phi2, phi4, phi1, phi3. And then we need to subtract kind of similar terms where 3 is replaced by 4. So that is essentially what happens, the way to get the second line in our definition. Okay, so that gives us kind of four expressions. And now let us notice the following properties of K naught. So K naught was kind of related to this residue pairing, and therefore K naught it kind of has a similar property that we observed for 3-point function, means that K naught is really defined on classes. So kind of it only depends on the classes of phi1 and phi2. So that's why in particular, if I kind of apply projection to phi2 and apply good section to phi2, so that wouldn't change the answer. So it will still be K naught of phi1, phi2. So and similar, I can do similar with the first argument. So the answer would be the same. So I still need to apply like projection in section, because in my definition I need to use like some representatives to compute. So therefore, instead of original function phi2, I can use another representative from the same class from the image of a good section to get the same. So that allows us to kind of rewrite this expression in the following form. So let me do it with the first term. So let me kind of put half here and do the following. So keep the contact term as it is, phi1, phi4. But for the second term, let me do a linear combination, like phi2, phi3, and this kind of good section projection of phi2, phi3. So I just used symmetry properties. And then we have, okay, 3 more terms of that type. So for each term, we perform the same trick. So we take like this, the argument that is not a contact term and kind of represented as a half of original argument plus another half that is kind of with addition, good section and projection. Okay, so now we would get like way more terms. So originally we had 4 terms. Now if we kind of expand the sums into individual terms, we will have 8 terms, and that kind of start looking a bit too much, like too many terms. However, that's kind of a way to prove. So now we will just eliminate some terms. So for K1 defined on this board, it has the following property. So K naught, by virtue of this definition, was symmetric in these arguments. While K1, given that we do some kind of different operations to phi1 and phi2, is actually anti-symmetric in its arguments. Phi side is minus K1 sine phi. So that is some kind of obvious property from this definition. So okay, but still not enough, because we have like K1s in derivative part and K0 in contact term. And however, there is a key kind of lemma that apparently K1 and K0 are related. And yeah, I need to erase something. Let me erase this kind of general construction. I think we are kind of familiar with what we computed. So I still want to put K1 and that kind of important lemma works in the following way. So if I take K1 of the following expression, so it's phi1, phi2 minus 2. good section of a class phi 1, phi 2, and kind of pair it with some phi 3. So that expression apparently equals to k naught applied to a compact term phi 1, phi 2, and pair it with phi 3. So in some sense, like this kind of higher residue pairing is like a pairing from a previous level, but applied to a contact term. So this formula is kind of can be explicitly checked because we have a definition. So, but due to lack of time, let me kind of skip a proof. Explicit check and kind of details in the lecture. Which I will post like later today. So okay, so given that relation between k naught and k1, it essentially allows us to trade like some of these expressions into expressions with k1. So and furthermore, we see that here when we expand it, or when we do this trick of kind of doubling and putting half, so in arguments of k naught, like the second argument, so one argument of k naught is like a contact term of some kind, while the other argument of k naught contains something related to a good section. So therefore, for example, this term, if we turn it to k1, so it will be 1/2 k1, and here what we do, we replace the first contact term into phi 1, phi 4, minus good section of the projection of phi 1, phi 4, and here we will have phi 2, phi 3, plus good section projection phi 2, phi 3. And then we will have three more terms, but these terms, they're kind of related to this first term by relating. So we first need to relabel kind of 2 into 1, and then we need to kind of relabel 3 into 4, and 2 into 1, and 3 into 4 done simultaneously. So that's our kind of with some signs that afford terms that we will use. And among these four additional terms, there will be some terms of the same structure, because, for example, if you relabel simultaneously 2 into 1, so let's look at this last abstraction. 2 into 1 and 3 into 4, so that will be like phi 2, phi 3, and here will be phi 1, phi 4. So this term, which is just k1 of phi 1, phi 4, phi 2, phi 3, so it will kind of go to itself, and furthermore the sign here, okay, the signs here will actually be plus here. And this term will be just eliminated because of antisymmetry of k1. That what we get exactly k1 of the same arguments, but they are exchanged at their places. However, for the second term, which is contact term, we will have not quite it, but yeah, okay. So therefore this term would vanish. Yeah, what about contact term? But for a contact term or for a terms containing good section, due to this difference in signs, it will not vanish, but it will double, because it will be like this term, and then this kind of plus sign, phi 2, phi 3. plus sign, okay, phi 2, phi 3, plus phi 1, phi 4, as b, and therefore when we exchange arguments, the things wouldn't cancel. Okay, so there will be some cancellation, some terms would remain, and the kind of among the remaining terms will be exactly this kind of two terms that are contribution from derivatives. So they wouldn't cancel, but they will rather double, and but later they will cancel with this derivative term. However, so kind of for derivative terms, yeah. So for kind of phi times phi terms, the terms that are not cancelled by antisymmetry, they will be cancelled by derivative terms. But there is no kind of such contribution for this good section and projection. So therefore, kind of at the end of the computation, not sure where to write it. Yeah, let me write it here again. So if after we add start terms, so what we will left with this kind of K1 applied yeah, so there will be two remaining terms, SP phi 1 phi 3, SP phi 2 phi 4, and plus the same type of term with 1 and 2. So that is kind of final result of this long computation. So what we did, we kind of computed derivative part, turned it into kind of K1 pairing between products of phi's. So then we took contact term parts, we turned it into K0 pairing. We kind of performed this doubling and kind of with a factor of half, introduced good section dependence for a second argument. Then we turned K0 pairing into K1 pairing by trading contact term into kind of product minus good section projection. And then we just kind of observed a lot of cancellations, and at the end of the day, we got this final expression that once again was the difference between computing 4-point function using expansion in phi 4 minus computing 4-point function using Landau-Ginzburg-Saito recursion in phi 3. So and what we end up into some contribution that is precisely of this form. That is kind of first side of pairing on some kind of specific elements from image of a good section. So therefore, if we demand that on any elements from image of good section this thing vanishes, that would be sufficient to kind of make the 4-point function symmetric. Okay, so for symmetry of a 4-point function, we need like this condition with the first pair, and kind of we can think of this f here as some kind of way of recursively defined higher order pairings instead of in terms of lower order pairings. So we can turn this lemma into some kind of definition where we define pairing at the level n plus 1 in terms of a pairing at the level n. So we know how to define contact term. So once again, to use this definition, we need to make sure that it's compatible with ambiguity of a contact term. So that is kind of, that's why let me call it predefinition, because that requires verification of correctness. And it turns out that we can explicitly investigate symmetry of 5-point functions. Let me. So we can do the same lengthy computation for a 5-point function. 5 symmetry. And it turns out that for 5-point function symmetry holds given the following kind of sufficient conditions. So sufficient conditions would be following. So first is kind of next level of side pairing like K2 evaluated once again at image of intersection. So that should also vanish for all side ones. Okay, so that was kind of in condition, but that's not the only condition that you will discover at the case of 5-point function. So there will be a second condition that kind of looks the following way. So if I deform my superpotential W, then let's say when I will express 5-point functions in terms of 3-point functions, I will get for a 3-point function some kind of contact terms that computed in deformed kind of from deformed when we compute deformed 4-point function in terms of deformed 3-point function. So and here additional condition is the following. So that such contact term should vanish. And here kind of phi is from image to intersection, while capital phi is just an arbitrary function. So and epsilon, okay, arbitrary parameter. So when epsilon is 0, so then this condition is kind of trivially satisfied, and that is something that we observe it multiple times, that if I take kind of contact term of just good section, so if product of two functions happens belong to good section, then this contact term vanishes. It vanishes for kind of simple reasons, because if phi is an image of a good section, then SW pi W applied to phi is a phi itself. So therefore, kind of I can choose my vector field to be 0 vector field, and kind of get one answer for a good section, which is 0 answer. One answer for a contact term, which is 0 answer, which is divergence of a 0 vector field. And here, like the symmetry of 5-point function kind of requires extension of this property. So it requires some kind of compatibility condition. So if I deform W in the direction of phi, then kind of a good section phi defined at W should also kind of change in a very particular way. So in a sense, this condition in a language of kind of Kyrgyzstan, it phrases the following way, that the good section, the image of good section, the image of the good section is some finite dimensional vector space which is spanned by kind of good sections applied to basis in Jacobi ring, and it's embedded in infinite dimensional space of holomorphic function. So and as we change superpotential, so this embedding of a finite dimensional vector space into holomorphic functions will also vary. And we want the image of a good section, and then we can describe this variation by introducing some kind of connection. So the image of a good section is transported with respect to a connection define it by contact class. So that is kind of formulation of this condition in kind of language of a good sections and in this Kyoji-Saito theory of a good section. That we need to kind of transport the image of a good sections if we change superpotential. And if we change superpotential in direction of capital phi, then we need to kind of modify our good section W by kind of transporting it in the direction of phi with this kind of connection fidelity. Okay, so that was kind of story of 5-point functions. And let me, in remaining like few minutes, and that part is kind of regularly proven in kind of one of the old papers by Andrei Lossev. Program. Old papers. And then kind of given these two conditions and given the fact that these two conditions match with the definition of a good section in Kyoji-Saito theory of primitive form. So we kind of conjectured. So here get level of conjecture. So conjecture is 10-point functions in LGS theory are symmetric. Given that good section obeys these two properties. So the first property is that all higher pairings like W, 5, 1, 5, 2 is 0, and here it's like for all n which is bigger than 0, so n is some integer number. Okay. For all n that belongs to z bigger than 0, all pair of functions phi 1 and phi 2. And then we need to kind of further modify this expression a little bit. So here we should also have this condition satisfied not for just given W that was part of Landau-Ginzburg-Saito theory. So there was but that should hold in kind of arbitrary family. So we can deform this W kind of in some direction. So we can kind of deform this W in the directions of Jacobi. So this kind of W of P is essentially like W plus T A phi A plus dot dot dot. So the kind of linearized deformation is in the direction of kind of good sections. So good sections of Jacobi basis gives us basis for deformations. And what we want, like as we deform W, so there will be a deformation of a projection, deformation of section, and we really want this first condition about vanishing of kind of residues hold for all W. And then the second condition is this condition of a parallel transport, and it is formulated in the following way. So let me look at kind of good section, apply it to some fixed basis in Jacobi ring, like phi b would be like a good section of some component or some basis element phi b as double some basis element eb from Jacobi ring. So if I want to kind of transport this good section infinitesimally, it is the same as computing a contact node between phi b. So all this kind of depends on this kind of good section at some w. And here you get dw. So this kind of conditions 1 and condition 2, so they kind of inspired by two ideas. They inspired by explicit computation by explicit proof of explicit investigation of a symmetry of 4 and 5 point functions. And they are also kind of inspired by Kyrgyz's theory of primitive form, where he got like a similar object kind of good section, and that similar object was kind of axiomatically was axiomatically defined as the one satisfying these conditions 1 and 2. So given that conditions 1 and 2 kind of give us what we need for symmetry of a 4 and 5 point function, so we kind of naturally conjectured that these two conditions kind of generalize to a kind of honest good section in the sense of Kyrgyz are just enough to make endpoint function symmetric. But that is kind of still a conjecture. So in kind of particular cases of a mirror, say mirror for CP1 or mirror for CP2, we can just kind of explicitly compute endpoint functions and see that they are symmetric. But in the general kind of Landau-Ginzburg-Saito theory, that is still a conjecture on our side, but that looks like a plausible conjecture. Yeah, so I think that's a point where I should really stop today, and kind of I will post, I think later today or tomorrow, I think homework on Landau-Ginzburg-Saito theory. Yes, and then starting next lecture we will kind of get into proof of a mirror symmetry. So far our lectures were like formulation of a mirror symmetry statement that Gromov-Eaton invariants match with Landau-Ginzburg-Saito correlation functions, and then we spent 2 lectures in kind of detailed into details of this Landau-Ginzburg-Saito construction, and that will be important for us later, because kind of later when we prove mirror symmetry, we need to kind of not only get some kind of recursion formula that is there in Landau-Ginzburg-Saito theory. So getting a recursion formula is pretty easy, but the hard part is kind of make sure that the kind of section in recursion formula it really obeys these 2 properties. So that would be kind of hard part, and to kind of argue why we should do that hard part and care about these properties. So I kind of talked extensively that these properties are kind of mandatory to make sense of Landau-Ginzburg-Saito theory. Okay, so yeah, I think it's end of the lecture today. Yeah, I think the April holidays, they are not affecting our lecture. I think it's May's holidays that they will move our Tuesday to some kind of weekend day. But okay, but for April holidays we are good. Okay.
Excuse me, explain a little bit. What do you mean by a connection here?
So connection means that it kind of gives you a way to to identify vector spaces that are images of a good section at different values of this parameter epsilon. So connection gives you a way to identify vector spaces. And that's what usual connection on a manifold is. So you have like some vector bundle, and connection basically tells you how the vectors how to kind of identify vector in kind of one section vector bundle. So in a vector space over one point to a vector in a vector space over different points. So here our kind of base is a space of deformations for W, just some finite dimensional space. And on this space, like we have some coordinates epsilon a, and for each point on this space, we have a finite dimensional vector space which is image of good sections. And then what we want to do, we want to see like what is the image of a good section like over some point where epsilon is non-zero. So we know the image of a good section over the point epsilon equal to 0. So the image as an embedding of this kind of finite dimensional vector space into space of functions. And then this equation basically tells us that to see the image of a good section, what you need to do, you need to kind of take a vector, like say collection of basis vectors at epsilon equal to 0, that we call this phi little phi b. And then for each such phi b, like if epsilon is infinitesimally small, then what you need to do, you need to compute a phi b contact term with this capital phi a. Capital phi a gives you like a vector, tiny vector that tells you in which direction you deform. So that's why you have like a way to transport the vector phi b along the vector like capital phi a on some kind of space of superpotential. And that's why it is a connection that space. So it gives you a way to transport vectors in some kind of neighborhood when epsilon a are small.
The term in the bracket is what you mean by a deformation of good section. Oh.
Yeah,
because phi b is
so good section is just a collection of functions. So your Jacobi ring is some finite dimensional object. So it has some finite basis. So that's why for each basis element you can define its image in a good section. So, and that will be like basis in that vector space that is image of good section. So therefore we kind of fix some basis in Jacobi ring, and then we see how the corresponding kind of images under good section that depends on W. So basis is fixed, but as W of t depends on t. And we want to see like, and so this phi b functions of t is like as W of t applied to some fixed basis vector in Jacobi ring. So, and that is kind of epsilon dependence or t dependence of a good section. So, and the good section is a function. So this function can kind of depend on a parameter t or parameter epsilon. So as we deform W in some particular direction.
So the term in the bracket is the orange term. You call it phi b.
Yes. So this whole expression, yes, that's what I would call phi b of epsilon. So I have like phi b of 0, and then as I change epsilon, so my phi b would kind of change. So now the image of the same kind of so for that you first need to prove that if you perform this what is called versal deformations, then your Jacobi ring doesn't change. So if your Jacobi rings are kind of canonically isomorphic, so then for Jacobi ring at different values of epsilon, you can choose the same basis. And therefore you can use this basis to kind of evaluate good section and to turn the information about good section into collection of holomorphic functions that depend on a point in the space of deformations.
Yeah, but somehow you hear it's like the phi a's here are like this partial W, partial T.
No, not quite. So partial W, partial T, it just gives you a kind of direction of deformation. So partial W, partial T is like a vector on a base.
Yeah, I mean this capital phi.
Yeah, so capital phi, yes. So capital phi, they're just like components of that vector. Yes.
Yes, this partial W, partial T lives in the ideal of defining ideal of the Jacobi ring.
Partial W, partial T. No. Jacobi ring, we take derivative of a capital Y. So it's not like elements of gradient ideal. So W kind of depends on two types of variables. We usually call them little y, usually capital Y and little t. So it's kind of like W of y plus some kind of formal series in t. And W of y is our mirror superpotential. And the Jacobi ring for different t is defined as kind of gradient ideal with respect to this y derivatives. So it's kind of, we have family of mirror superpotentials.
Yeah.
So in this
and this T is different from the Q,
right? Yeah. Okay, so in general, yes, this T is different from a Q, but there is like some smaller subset of T's whose kind of deformation can be related to Q deformation. So
yes, because here it's like T is the same as
generally you have like way more T's than Q's.
Okay.
So and there is like a special subset of T's that can be kind of recasted into deformation of Q.
If we need some restriction for this deformation of superpotential.
Yes, so that is what people call versal deformation. And restriction is essentially such that your Jacobi ring kind of stays the same. So it's kind of simple to formulate for a polynomial superpotential. If your W is kind of polynomial superpotential like xn plus something, so then versal deformations are kind of deformed by monomials of lower degree. That essentially the number of roots doesn't change, but the roots move somehow. So however, in non-polynomial case, it is a bit more tricky way to define this versal deformation, but it can be done. So therefore here, yes, strictly speaking, the space of deformations is a space of versal deformation. So it has the same dimension as Jacobi ring. So while space of arbitrary deformation for holomorphic function is like infinite dimension. And here we are looking into special finite dimensional subspace that preserves the Jacobi ring.
You mean this theory is very free to choose W?
Yes, so in this kind of setting that we talked today, there was like nothing, we kind of never used mirror superpotential. So any superpotential would do for this theory, and it will still define you some kind of endpoint correlation functions, and furthermore, these endpoint correlation functions can be used to construct a solution to WDLE. So for that part, in kind of polynomial superpotential, that's what people usually call singularity theory. So when you have polynomial superpotential of multiple variables. And here we discussed the singularity theory in even more general setting when W is not polynomial. So that's why here there was nothing specific about being mirror to something. However, we kind of expect that if we kind of perform carefully mirror map, then we will land into some kind of consistent Landau-Ginzburg-Saito theory. That from a mirror, we would get like a good section that obeys these two properties. That we don't need to kind of derive it in a general theory, but it will naturally come with a mirror. And that is something that was not done in the literature properly. That people kind of computed mirror superpotential and kind of wrote down 3-point functions, became happy that 3-point function, like the 3-point function given by residue formula matched with quantum cohomology, and that was kind of great success. But to really kind of get a mirror map for all Gromov-Fit invariants, we need to define a good section, which is in general setting for general Landau-Ginzburg-Saito theory, should obey these two properties, and kind of we will see that mirror construction, it will naturally contain some kind of section, and in this section we will verify that the section from a mirror construction obeys these two properties. So that still leaves us with a possibility that maybe the solution for good section for these two properties is not unique, and in the general theory, like if we don't know anything about mirror, there might be like, I don't know, different consistent ways of defining correlation functions, and furthermore, maybe even correlation functions are kind of different for different choices of good section. But that is something that it's kind of, I think, unknown in the literature when you have like more than one variable, and that's why it is important to get a good section from a mirror in case we need some kind of distinct good section in kind of family of solutions to these conditions. If it's more than one, it's important to know which one kind of associated to mirror and which one is just a consistent for Landau-Ginzburg-Saito theory. Yeah. Okay. So we kind of over time. Okay. So thank you. Sorry for going over time. Yeah, and I think Bowen will post videos, at least for previous two lectures today. Today he'll post links in WeChat.
YouTube.
Yeah. So sorry for kind of not posting. Okay.
因为他定义的时候感觉都是乘起来的。